So, good afternoon everybody. In the last class we were looking at different types of minerals that were present in rocks which were used as concrete aggregates, and some of the tests for identification of minerals you have already done in your lab classes, like scratching the aggregate with steel, scratching the aggregate with glass, looking at the streak that the aggregate makes on a porcelain plate. So, all these are regular test methods for identification of different types of minerals present within rocks. So, there are different types of minerals that are found in different rocks which are used as concrete aggregate, and because of the presence of these minerals you sometimes get unique properties from the aggregate when you use them in concrete. So, the silica based minerals that you find are quartz, opal, chalcedony, tridymite, cristobalite. So, these are different forms of SiO2. Okay. You all know very well that quartz is a highly ordered form or highly properly arranged form of SiO2. It is crystalline, it is hard, it is weathering resistant, and in some cases if the quartz has gone through very high temperature and pressure, it may result in having a strained form. That means the bonds may get strained, that may lead to the material getting some reactivity. Okay. Typically quartz is not reactive at all, it is highly inert, it is very hard and crystalline, but you may get certain forms which, especially the ones in metamorphic rocks, which may end up being quite reactive as far as alkali-silica reactivity is concerned. Anyway, we will talk about ASR specifically towards the end, but in general quartz is known to be not reactive, but then it can in certain types of rocks. Okay. Opal is a hydrous form of silica, okay. It is SiO2, it is written as SiO2 NH2O, that means it has got some waters which are bound within the structure of the silica, and because of this structure the ultimate structure of the opal becomes amorphous, and that leads opal to have a very high reactivity with respect to alkali-silica reaction. Chalcedony is a fibrous form of silica. Again, it has a high range of disorder which makes it more reactive, and in cases of ASR you would do well to avoid opal and chalcedony minerals which are present in your aggregate, but sometimes these could be present as minority minerals in your aggregate irrespective of what you are trying to use. So, you have to be careful about your choice of aggregate and make a proper assessment as to how much of it would be made up with opal or chalcedony. Tridymite and cristobalite are high temperature forms of quartz, especially when you have heat treated your material to around 800-900 degrees Celsius, you most likely would get other forms of quartz like tridymite or cristobalite. Now, these could be ASR reactive. So, what happens now is you have igneous and sedimentary rocks that may have quartz, but when these rocks undergo metamorphosis, you can get extremely high temperatures and pressures exerted on these rocks, and because of this your structure, crystalline structure will get strained. Your forms of quartz that are actually available may get transformed into cristobalite or tridymite. So, ultimately the metamorphic rocks that end up from the same inert passive igneous or sedimentary rocks may actually end up being reactive. So, very often, although we see that igneous and sedimentary rocks may not have sufficient reactivity, the metamorphic form of the rocks have a lot of possibilities of reactivity. I am talking about the type of rocks which are made up with this silica based minerals. However, having said that, I should also add that opal and chalcedony are also often found within sedimentary rocks, which makes sedimentary rocks also of certain types fairly reactive. Okay. Like for example, I will talk later about a rock called grey wacke. It is a sedimentary rock and that is known to be quite highly reactive. Okay. Feldspars are basically sodium or potassium silicoaluminates which are found, or even calcium silicoaluminates which are found primarily in igneous rocks like granite for instance. So, the potassium based feldspars are also otherwise called as orthoclase or microcline. Sodium based feldspars are including albite and plagioclase, and calcium based feldspar is called anorthite. So, different types of silicoaluminate species exist within igneous rocks, and these are essentially called as feldspars. You also have ferromagnesian minerals like hornblende, augite or biotite. These are basically iron and magnesium silicates. Micaceous minerals are the ones which introduce very different kind of a characteristic as far as mechanical properties of the aggregates are concerned. So, you have foliated properties because of the presence of micaceous minerals. Foliation means you have basically layered formation of the rock. That is primarily because of the micaceous minerals which include muscovites, biotites, chlorites or vermiculite. You also have clay minerals, which are basically layered silicates, extremely fine layered silicates. Clay minerals are extremely fine, of course, you know that, less than 1 micron in size. The typical clay minerals include kaolinite, illite and chlorite. These are quite stable, but they could absorb to a large extent a lot of water. Kaolinite does not, but illite and chlorite are known to absorb some moisture. Smectite and montmorillonite are highly swelling and unstable clays, and of course, you need to ensure that if they are present in your aggregate, you need to minimize their usage as much as possible. Okay. Zeolites are naturally occurring hydrated aluminum silicates, okay, which could be soft and light colored, and what happens is sometimes these zeolites can also result from the transformation of the rock. Certain types of minerals within the rock can get transformed to zeolites, and these are essentially soft minerals. We need to avoid aggregates which have too much or an excess quantity of zeolite present in them. Okay. Carbonate minerals, you all know very well, include calcite and dolomite. Calcite is calcium carbonate and dolomite is calcium magnesium carbonate. Okay. These are again soft, but then they also form very good aggregate for concrete, apart from obviously being the primary raw material for the manufacture of cement. And carbonate rocks are acid soluble as opposed to silicate rocks, which are not acid soluble, and this is something that you have already done in your laboratory classes before. Iron sulfide minerals include pyrite, marcasite and pyrrhotite. Now, the iron sulfide minerals, although they form very hard aggregate, the issue there is that the presence of sulfide, in certain conditions, that sulfide can actually transform to sulfuric acid. It can give rise to sulfuric acid, and this was actually found out by accident when pyrite based aggregates were used in concrete, that the reactions with the alkaline medium of the concrete led to the formation of sulfuric acid from the pyrite aggregate, and that led to obviously the damage of cement paste by acid attack. Okay. So, again you have this tendency to attack concrete and stain it because of the formation of this acid. Iron oxides include magnetite, hematite, ilmenite and limonite. Again, most iron oxides are heavy in nature, so they form mainly the components for high density concrete. When we want to use high density aggregate, we basically use iron based aggregate for concrete. So, some pictures of common minerals. You have orthoclase, albite, biotite. Okay, these are all orthoclase and albite are basically feldspar minerals. Biotite is a micaceous mineral, right? Calcite, of course, you know, calcium carbonate. Chalcedony, you can see the irregular structure that it is showing, and chlorite. Okay. So, these are all different types of minerals that you can actually get in the natural environment. Hornblende. Now, look at pyrite, it looks almost like gold, so it is called fool's gold. Okay. That is the material which is iron sulfide based mineral actually, copper iron sulfide. Okay. Quartz, you can find fascinating pictures of quartz on the internet, of course. This is one of those pictures that I picked up from Wikipedia. Quartz is a very hard mineral, it is a very inert, mostly inert mineral. And opal, of course, you know that opal is also used a lot for jewelry, manufacturing jewelry, but opal is essentially a form of silica. Okay. And kaolinite, this is a microscopic picture of kaolinite, which shows you the very fine texture of kaolinite and also several layered aluminosilicate sheets which are connected to each other with some waters of hydration inside. Okay. So, kaolinite, of course, you know also that when you heat up kaolinite to beyond 700 to 750 degrees Celsius, the water between the sheets gets removed and the sheets get activated. So, in other words, the clay becomes activated clay or calcined clay, which is quite useful as a pozzolanic material, and you can replace up to 25-30% of your cement with calcined clay, especially the kaolinitic clays. Okay. We will talk about that, of course, in more detail in the mineral admixtures chapter. So, these minerals make up the rocks. So, rock is composed of either one type of mineral or several types of minerals. Okay. So, rocks, you know, are of three different types. You have igneous, sedimentary and metamorphic. 95% of the outer 10 miles of the earth's crust is composed of igneous and metamorphic rocks, but 75% of the rocks on the earth's surface are sedimentary rocks. Okay. So, you can imagine that when you are actually extracting from close to the earth's surface, you are mostly going to get sedimentary rock. If you want igneous and metamorphic, you need to actually dig down deeper. For example, granite, for instance, you need to have a quarry that goes fairly deep to actually extract granite. Limestone, you may be actually getting surface limestone mostly, because mostly what happened is limestone and dolomite formations were from sea floors, ocean floors, and essentially the shelled organisms basically started depositing their calcitic sediments, and under the action of the pressure of the sea water and with the passage of several years, these the shelled organisms got compacted into what we know today as calcite or limestone. Okay. So, essentially we are looking at prehistoric shelled organisms which are actually transformed into this, or which are lithified into stone. So, igneous rocks we know very well are those which are formed from the molten lava. So, molten lava cools and forms different types of igneous rocks. Depending upon the rate at which this cooling occurs, you get different types of igneous rocks. If the cooling occurs within the earth's crust, it occurs slowly, and so you have the chance to form very large crystals. That is typical of the intrusive igneous rocks, which include granite, gabbro and pegmatite. Granite is the rock which is found in abundance in the southern part of our country, and this is where we see that the granite has actually very nice and big crystals. You can actually see nice crystalline materials in granite, and granite is also a very hard material, useful for concrete applications obviously, but also useful as a roadway material for asphalt concrete. Pegmatite is a material which has extremely large crystals, much larger than granite, and that may often turn out to be a disadvantage with respect to intrusive igneous rocks, that if you have very large crystals and you are using it for applications which involve abrasion, you can imagine that these large crystals can get dislodged quite easily when you abrade them. So, pegmatite is not suitable for applications such as highway construction. Extrusive igneous rocks, when the same molten lava cools on the earth's surface, the air cooling that happens is much faster, right. So, because the cooling is faster, you result in the formation of much finer crystals, like in the case of basalt, andesite and so on. Okay. So, these are smaller crystals, but they are not yet at the level which could be reactive. However, some forms of these extrusive igneous rocks, some forms of rhyolite or andesite could be reactive, because the cooling may have been fast enough to result in some degree of reactivity in these materials. Of course, the most reactive are the pyroclastics, which are essentially the cementation of the ashes that get spewed out during a volcano. So, mostly we know these to be producing very good lightweight aggregates like volcanic tuff or pumice or breccia, but these are also composed of amorphous silica, which may lead to a very high degree of reactivity if you use them as aggregates inside concrete. So, alkali silica reactivity will be very high in the pyroclastics, but for the most part we are concerned about the andesitic and rhyolitic rocks, which may have high alkali silica reactivity owing to the fact that they have very small crystal sizes. Sedimentary rocks of course are deposited in a fluid medium due to lithification of weathered sediments. So, any sediment that gets weathered and gets compounded together either by the action of pressure or by the action of additional cementing materials like iron oxide or calcium carbonate can form a sedimentary rock. Okay. So, lithification can occur because of cementation, common cements being iron oxide, quartz and calcite, and the other reasons could be crystallization from like deposition of the crystals in one location, or compaction because of high temperature and pressure. Typical sedimentary rocks are shale, sandstone and limestone, which make up nearly, of course if you add this up it becomes 100%, but close to 100% of rocks which are found are belonging to the shale, sandstone and limestone category. So, you have sandstone of course is used a lot in monuments in northern part of India. You have different colored variations of course. The pink ones or the red ones are the ones which contain iron oxide as a cementing agent. The white or yellow sandstones are the ones which contain calcium carbonate or calcite as a cementing agent. So, this is a picture of a quarry where they have actually extracted limestone. What is interesting to see is you can see the bed is actually inclined. The deposition of limestone is happening in an inclined bed. You can see those much clearly here, right. So, essentially limestone deposits are formed because of the decay and redeposition of calcite from the shelled organisms that happens over many millions of years. Okay. We are not talking about tens or thousands or hundreds of years, we are talking about millions of years. Okay. And over this time there is a lot of pressure that is exerted by the weight of the seawater above that leads to the compaction of these calcite crystals into limestone deposits. And interestingly, you can also find fossilized remains of the shelled organisms within the limestone deposits. So, it is quite interesting to see this, because if you visit a quarry, you can also be doing some archaeology for instance. Metamorphic rocks are formed when pre-existing rocks are modified because of the application of temperature and pressure. And the important part for us to understand is when very high temperatures and pressure act upon the originally pre-existing rocks which are igneous or sedimentary, these can lead to a recrystallization and form a completely different structure compared to what was originally present. Okay? And that is the reason why metamorphic rocks are quite difficult to ascertain whether they are going to be useful as aggregate or not, or whether they are going to cause any problems like alkali-silica reactivity or not. Okay? So, examples of metamorphic rocks, you know, are marble, which is metamorphosed form of what? It is limestone, basically limestone which gets metamorphosed to marble. You have gneiss, which is granite, right? Schist is usually from micaceous rocks. Okay? Phyllite, slate is basically the metamorphosed form of shale. So, these are all different types of metamorphic rocks that you can find on the earth's surface. And again, because of the recrystallization, you end up usually with very large crystals and with a well defined cleavage. That means that these rocks would have definite boundaries of failure, of fracture, because of the formation of the large crystals with well defined cleavage. So, what you need to ensure is you minimize the usage of rocks which can have these kind of properties, because then they would present very weak or layered rocks which may not be suitable as aggregate. So, let us again put whatever we have discussed into specific understanding about how concrete properties can get affected by the geological nature of the rock. So, alkali-silica reaction obviously is the most important consideration when choosing a certain type of rock for your concrete aggregate. You know that we have a pore solution in cement paste which is highly rich in alkalis, and these alkalis are available to react with the reactive silica that can be present in certain type of aggregate. The entire mechanism of ASR we will discuss in a later chapter, but essentially fine grained siliceous minerals in igneous and sedimentary rocks are susceptible to reaction with alkalis which are released from the cement mostly. Okay? So, amongst igneous rocks, the ones which we need to look out for are rhyolite, andesite, and also the rocks obviously which contain the pyroclastic minerals or the volcanic glass. Okay? And in these cases, the principal reactive minerals which might be forming are the opal and chalcedony. So, opal is the hydrous form of silica and chalcedony is the fibrous form of silica. Okay? These are highly amorphous, very reactive, and these can lead to extremely high levels of expansions in your concrete when you have a high alkali environment. Among sedimentary rocks, the ones which are most reactive are chert and greywacke. Again, chert and greywacke can also contain opal and chalcedony as minerals. Okay? Please remember, these are rocks, chert and greywacke are rocks which contain alkali reactive minerals in them. It is the minerals which makes the rock reactive. Okay? Among metamorphic rocks, the ones which we are most careful about are phyllite and argillite. This is because of the presence of strained quartz. Okay? So, as I talked about earlier, quartz is a highly crystalline material, hard and inert crystalline material, but the problem is when high temperatures and pressure act upon quartz, you can strain the structure, and that strains can induce actually some reactivity into quartz. Okay? So, because of that, metamorphic rocks may have a lot of susceptibility to alkali-silica reaction. So, again this table actually captures the different forms of or reactive components present in different types of aggregates and their relative abundance around the world. So, abundance is important because we know that we have to use aggregate which is locally available, right, and based on that we need to understand whether the aggregate that we have can contain some of these reactive minerals or not. So, the first column shows you the reactive components. Of course, you have opal, which is the hydrous form of silica. You have silica glass, amorphous silica basically, chalcedony, which is fibrous form of silica, tridymite and cristobalite, which are high temperature forms of quartz, and quartz itself when it is present in the strained form. Okay? So, degree of crystallinity is also represented here. Opal, silica glass and chalcedony are almost amorphous. So, chalcedony is not entirely classified as amorphous, but it is a poorly crystallized form of quartz. These forms, tridymite, cristobalite and quartz, are all highly crystalline, okay? But the fact that you have a strained structure because of very high temperatures leads to the alkali-silica reactivity. The types of rocks in which these types of minerals are found, of course, the opal is found in limestone, cherts, shales and flints. Silica glass can be found in rhyolite, andesite, volcanic glasses and so on. Again chalcedony mostly in sedimentary rocks, okay, and tridymite in opaline rocks, and quartz can be found in quartzite, sandstone, sometimes even granite may have quartz that is actually reactive depending upon the extent to which granite has been modified by high temperature and pressure. So, if you use the metamorphosed form of granite like gabbro or gneiss, you might actually end up having some reactivity in it. Abundance widespread as far as opal is concerned. Now, of course, abundance of silica glass is mostly in river sand and gravels. Chalcedony is widespread. High temperature forms of quartz like tridymite and chrysoberyl could be rare. So, that is something we don't worry about that much. Strained quartz is quite common in most metamorphic aggregates. So, again these are present all across the world. So, aggregates have to be screened very carefully for their potential reactivity before we can consider them suitable for use in concrete. Okay. Now, sometimes this alkali silica reaction could have a carbonate counterpart in alkali-carbonate reaction. So, this is a reaction which happens when you have carbonate rocks like limestone and dolomite, which could react especially when they have very large amount of clay bearing minerals. Now, this is a little bit of a difficult problem to understand because the reactions are not very well understood in terms of how they actually lead to expansion and formation of cracking in concrete. But for the most part we know that there are certain types of textures which are exhibited by carbonate rocks which can lead to high degree of reactivity in an alkaline medium. So, we will not talk about this in more detail. There are other considerations obviously when we choose aggregate for concrete purposes. Again, we talked about the fact that certain types of intrusive igneous rocks may have very large crystal sizes which may render them having a very poor abrasion resistance, because these large crystals can get dislodged quite easily, especially when you have pegmatite based aggregate. Metamorphic rocks may end up having micaceous or flaky and elongated pieces. If you crush metamorphic rocks, you will end up with a lot of flaky and elongated pieces. And obviously, you know that flaky elongated pieces will lead to reduction in the workability and strength of the concrete. Okay. So, these flat pieces will trap water inside, because of which workability will be lost, and secondly because if a fracture goes through the concrete, if you have a flat and elongated piece, it will easily fracture and crack, which will lead to reduced strength also of the concrete. And foliation is another problem which you find in metamorphic rocks, because you have this directional or rather layered arrangement of several types of minerals that leads to again weaknesses. Some directions are weaker as compared to the others. Again, soluble and soft minerals like zeolite could be present in igneous rocks, so you need to be careful. The other aspect is the presence of clay. Sometimes when the sedimentary rocks are chosen for concrete aggregate, you may get a lot of clay inside, and the clays obviously are to be avoided, because first of all they are swelling. Some of the clays are swelling type, the others can actually coat the surface of the aggregates, reducing the paste aggregate bond. So, again there are several reasons why you want to avoid a lot of clay inside the system. And sometimes when you collect from sedimentary sources like riverbed, you may actually get a mixture of different types of minerals, and some of these minerals could be highly porous, low density materials that may again reduce the strength of your aggregate. So, you need to do a proper screening. Now, interestingly, the way that the aggregate is screened from a riverbed is quite interesting. You have to collect a sample of nearly 200 pieces of the aggregate. You have to go through each one megascopically. That means you have to evaluate each aggregate piece visually, and then of course do the kind of mineral test that we already talked about previously. You need to then fraction it into the components that is regular density. That means what do you expect the density of aggregate to be typically? About 2.7 to 2.8, around that would be the density of most aggregate, right. So, you have to remove from these aggregates the pieces that you consider to be of low density, and your ASTM or IS, they tell you that the extent of deleterious materials or poor quality materials in your aggregate should be limited to a certain fraction, typically 5%. Okay. So, from these 200 pieces of aggregate, you need to remove those which are of poorer quality. Then you have to do further tests on them to identify what are the problems with them. Do they contain clay? Do they contain high porosity? Are they likely to be alkali reactive? Okay. So, it is a procedure that is quite highly involved, and there are people who are trained to do this kind of a petrographic evaluation of aggregates. Now, again in certain types of sedimentary rocks you may have cavities and conduits, especially when limestone and dolomite are used. So, you know, again want to avoid them because they will give you pathways for water to penetrate, and secondly they will also make the aggregate quite weak. So, choice of aggregates has to be done carefully based upon first of all presence of reactive minerals, then secondly the engineering characteristics exhibited by the aggregate. Most of these you will be able to pick out when you do the regular aggregate tests like specific gravity. You also do the aggregate tests which involve the measurement of the crushing strength, right, and also the impact value, aggregate impact value. So, all those will tell you the extent of hardness that the aggregate has. Los Angeles abrasion test is another common test for the aggregate, where you put it in a drum and rotate it for several revolutions. The idea is upon abrasion between with each other and also with the charge that you put inside in form of steel balls, you start losing some material from the aggregate. If the aggregate loses a lot of its mass, then obviously it is not a very durable aggregate in the system. Okay. So, with that we come to the end of the chapter on aggregates.